Welcome everyone to my notes on forces. So today and the next several days we're going to talk about forces, and taking a set of notes is a good way to start. So first of all, let's title our set of notes Forces. That's a really great place to start, forces. And this is what we're going to talk about. So let's start with the definition. I'm going to skip down one line and write the word forces, and let's give it a definition. Forces, that is an action exerted on a body. Now when I use the word body, that's another one of those sort of general sciencey words that means just like an object, right? Just an object. So forces, an action exerted on a body in order to change, and that's the big word there, to change the body's state of rest or motion. And this becomes really important. And of course, when we use the word rest, what we're really talking about is something that's not moving. All right? So let's give an example. Example number one. A skateboarder moves due to forces applied by the foot. And this is something that's very familiar to us, right? You want to ride a skateboard, you put one foot on the deck of the board, the other foot is kicking off, and you're pushing, and the skateboard moves. Second example, example number two. A soccer ball sitting on a field, soccer field, which means it's at rest, not moving, moves once a force is applied. And of course that force would be, typically a foot kicking, right? So that one's pretty familiar to us as well. So forces. And those forces, and we'll write this at a later time, can be a push or a pull, but we'll get there. All right, so let's talk about one kind of force, and these are balanced forces. And this becomes really important. Balanced forces. Life needs balance. Forces need balance. Balanced forces do not, let's do two underlines, do not cause an object at rest to start moving, or change the motion of a moving object. All right, so let's think about this. Balanced forces do not cause an object at rest to start moving or change the moving of this should be motion, change the motion of a moving object. So if I have an object right here that's at rest, if the forces are balanced, it'll always be at rest. It won't move. But as soon as I apply a force, of course, something happens. And if an object's flying through the air, some force has to act on it in order for it to not fly through the air. So if you've ever been to a baseball game, the batter hits the ball's flying through the air, an unbalanced force, typically a mitt, stops the ball, and so that is an unbalanced force. So let's go on to unbalanced forces. Unbalanced forces. We'll move this up a little bit so you can see better. unbalanced forces. Now this is different. Unbalanced forces will cause an object at rest to start moving or change the motion of a moving object. And an unbalanced force can be a push or a pull. So let's think about this. If a soccer ball is just sitting on the field, not moving, then all the forces acting on it are balanced. But as soon as you apply an unbalanced force to that soccer ball, it'll start moving. And that can be a push or a pull. Typically, the soccer ball, you would have applied a push or a kick, and the soccer ball moves. And that soccer ball is going to move once you've applied the force until an unbalanced force changes its direction of motion, which would typically be a headbutt, another kick, or even landing on the field, the ground applies an unbalanced force. And so we have balanced forces that don't change an object at rest or an object in motion. Unbalanced forces change an object at rest. You kick it and it starts moving, or as an object's moving, you apply an unbalanced force and it changes its direction. Now, we have to move on to a little bit different subject, and this is there are special units within the metric system that we use for forces. So let's write down the SI units, which again is French, I believe, for System International. So the System International units, or metric units, of force is the Newton, N-E-W-T-O-N, and we abbreviate that with a capital N. And of course named after Isaac Newton, not the fig Newton. But the unit of force for a Newton is a kilogram meter per second squared. Or you can write it kilogram meter per second per second. That is a unit of a force. And we'll get more into that, and eventually we'll even calculate those forces, so you'll see how the units come from. Just a little bit more and we'll be done with these. Now, when we talk about forces, the way we represent them is with an arrow, and we have to sort of be introduced to a new word now, and that is something called a vector. And a vector is a visual or graphic way to show force. And we're going to draw some vectors in just a minute, and then in a couple days we'll have lots of practice with force vectors. So a force vector has two components, two parts of it. One is magnitude, which is really a word meaning size, and one is direction. So a force vector shows both direction or magnitude and size. All right, and let me give you a couple of examples. So here's a force vector that shows a force of 2 newtons to the right. Here's a force vector that shows a force of 5 newtons to the left. Or we can even have one that says, hey, I'm going to do 3 newtons downwards. So you got to think about if you just had like a grocery cart, you could push it, left, right, you could push up on it, you could push down on it, but you would be applying a force vector. And we are even going to extend that idea just a little bit more, and we're going to talk about how to do math with our force vectors. And so here we go. Here's some examples of adding and subtracting force vectors. If you have 2 force vectors that are going the same direction, And in this case, I have two force vectors that are both 2 Newton forces. They are additive, meaning they add up, and they result in a new force that is 4 newtons. So if the two forces are going in the same direction, they add. And you think about that, if two people were, let's wait for the bells. If two people were pushing on an overly loaded grocery cart at Costco, and they each pushed with 2 newtons of force, they would add up, and that cart would move better with 2 people pushing with 4 newtons than a single person pushing with 1 2-newton force. That makes sense to us. And another example would be if I had a 3 Newton force and a 2 Newton force. That would give us a resultant vector of 5 newtons. So it's important that we put the dot, the arrow, and then we label it with what force it is. Now, in both of these cases, you have force vectors that are going the same direction. But if you have force vectors that are going opposite directions, so here's a 5 Newton force to the right, and I have a 3 Newton force to the left. What happens is you subtract the little one from the big one, and the resultant force vector would be 2 newtons to the right. And I'll do a demo in class that will help make this a little bit clearer. And for nearly our last one, let's do one where we have a 5 Newton force going to the left, and we have a 3 Newton force going to the right, and then we have another 3 Newton force going to the right. So now I have a total of 6 newtons to the right and 5 newtons to the left, and the resultant force vector will be a 1 Newton force to the right. Because these two added up, and you make 6, take the smaller one away from the bigger one, and the resultant goes to the right. And here's our last one. If we have a 5 Newton force going to the right and a 5 Newton force going to the left, the resultant would be 0 newtons, which would give us a balance. These forces are balanced, 5 to the left, 5 north, and 5 to the right and 5 to the left gives us a resultant of 0 newtons, which means we have no motion because we have balanced forces. I hope you got all of that. Please feel free to go back and listen to parts of it again, but this will be very useful for us when we get to class. Thank you so much for listening.